Okay, we got a big subject today, the heart of the Color Computer 3. This is probably going to be longer than what I would like for it to be, but this is something we really need to understand. So let's see if we bring up the right screen here. Okay, memory in the MMU. It's the heart, as far as I'm concerned, the heart of the Color Computer 3. So we've got a lot of things to talk about. It's going to be a lot of confusing stuff, but hopefully we'll get through it in a relatively short time. Okay, well, let's do some history of Color Computer 1, 2, and 3. So basic things. Okay, we know that we got 64K, and it's laid out in 8K chunks. Okay, so 8K chunks times 8 is 64K. Okay, and that's what we got right there. And when you start the computer up, this is what we're going to see. It's all 1, 2, and 3. We'll see some system stuff down here in the first chunk down around address 0. Our memory work area, and these three next chunks or blocks. I should call them blocks instead of chunks. Then we'll find extended basic, color basic, disk basic, and extended super basic on Color Computer 3. Won't have that on 1 and 2. The rest of them will be exactly the same. So let's look at some of these individual blocks. First one is a system block. Right? There's a system work area, I'm calling it. It's down around address 0. And from 000 up to hex DFF, all kinds of stuff. It's a direct page, system variables, interrupt vectors, all the inputs from the disk, the keyboard, the cassettes, floating point work area, low res text screen, which is at hex 400 to hex 5FF, and lots of other little bitty items that's down there that the basic, disk basic, extended basic use in order for the system to run. Above that E00 up to 1FFF is you're pretty safe at starting your assembly language programs in there. I think if you get lots of files open in disk basic, it might work its way up in there, or if you're not using sequential, you're using direct access files that may get up in there. If you're using a lot of files, I'd stay up above E00 and start at 1000, but you're pretty much safe to start your assembly language programs there. Right, the next block we're going to look at is this block here with no name or title to it. Okay, and this is when you load a basic program with the load command, or if you say new. Now in this Color Computer 3, I'm not sure if it's the same as on Color Computer 1 and 2, I don't recall, but on a Color Computer 3, that new command or load command will bring the program in at hex 2601. And all the reason I put that in for is if you write an assembly language program and all it is assist your basic program to speed up some calculations, whatever, and you want to jump to a assembly language routine, don't load it at hex 2500 because it will overload your basic program, and it will be disastrous. So just be aware that that's where basic programs are. Right. The next area is that's work area 4000 to 5FF. So our next block we're going to look at is this 6000 to 7FFF. Right. That's where the system stack is. Okay. The stack. If you don't know what the stack is, you need to read about it. But it's where important information for the system to work. Okay. Like in basic or in assembly language, if you go to a subroutine and you at the end of it you say return, you got to store that address somewhere where to return to, and that is kept on the stack regardless if it's basic or assembly language. And that stack is usually somewhere around 7F20. And I say that with caution because if you're in basic and you do clears 500, that stack line is going to come down farther. Or if you have lots of variables, lots of string variables or arrays, that stack line is going to come down. Just something to be aware of, nothing to do what we're doing, just so we're reviewing how the system works. Next one we'll look at, we'll skip extended basic because it's pretty much hard in place. Color basic, same way. We'll take a look at disk basic. And the only reason we're looking at it is because disk basic, it starts at C00 and goes up to D8CD, which means this is all open space in between D8CE and DFFF. There's 1,842 open bytes where you can stick some stuff in. I know in my system, I've got all kinds of stuff that I do, current date and different. I've got a lot of stuff stored up in that open area. So it's just there. Again, just a review of the systems 1, 2, and 3. All right. Now, you notice I changed the title up here. It doesn't say 1, 2, and 3 anymore. It just says 3 because that's where super basic is, up at E00 to FFF. And we'll take a look at that. Okay. It goes up to FA0B, and we have 1,012 bytes up there that is unused. Now I got the 4 stars here, down here, and what's in that area is the secondary interrupt vector area, high-res and graphic variables. Okay, remember back when we was prior lessons we was doing the locate and print line and things of that nature. Well, all them variables, and a good one was our graph, our attribute. Remember that our graphic? It was stored at FE08, if you recollect, was in our comment includes. Well, FE08 is inside. All the variables for the graphics is stored in there. So we'll look at them more better. That didn't even sound good. We'll look at what's in there in the future, and the input-output area is what the system uses. It can be changes regardless what you try. I mean, you can input and output there, but it always stays intact. Okay, now to the heart of the system. That was just a review of what the systems look like, just so you need to be aware of what it looks like if you're going to do assembly language. Now let's look at the memory managed unit. Okay, just a little bit of review here. The 6809 can only address 64K of memory. That's it. There's no other way around it. That's just what it's built for. It only has 8 address lines, and it's 64K. That is it. In order to access more than 64, the Gimme chip will perform a memory management function for us. Okay, well, we're going to explain what that does shortly. Right, the Gimme chip allows 512K of RAM to be accessed by the COCO 3. This is physical RAM. When I got that in quotes, because physical RAM is something you can put in your hand. You can pull the chips out. Well, there may be soldered, but you can pull the chips out and you actually hold them. That's physical RAM. It's there, and it's broken down in 64 blocks of 8K each. The 128 color computer 3 only has 16 of those physical blocks. And from that pool of the 64 or 16, depending what size machine you have, you need to select 8 of them to comprise the 64 address range that the CPU can handle. Right, the 8 blocks you select are going to be placed in MMU registers starting at location FFA0. Well, if you're confused, that's okay. But if you've never heard this before, I know it's got to confuse him, but we're going to take a look and hopefully straighten it out. At startup, the MMU will look like this. Wow, that's an awful lot of numbers, isn't it? A lot of stuff, okay? And I don't believe you're going to understand it until we get through with this and you come back and say, oh, I understand that. The only thing on this screen that you're probably familiar with is this one here that says CPU address, because we just talked about that. Those are different blocks. Core 0, 1, okay, up through where our super basic was up here at E00. Right, we got physical address. Physical address is, again, that physical memory you could hold in your hand. These are the physical addresses. When the system starts up, we'll get there. And the logical blocks and the block numbers and the MMU registers what they have in so that the system will work for you. Okay, let's look at the column on the right, starting down here at the bottom at hex 00, working our way up 1, 2, 3, 4. And I didn't put them all in there. You can probably count as good as I can from 5 up to hex 2F. And we'll start here at hex 30 up through hex 3F. Okay, hex 3F is 63. Okay, so at 0 base, 0 through 3F is 64, which is, we'll go out here to this calculate, this formula here is 64 blocks at 892, or 8K per block is 5,224, 288, or a hex 80,000. You divide that by 1K, which is 1024, and you get 512K machine. That's how it becomes a 512 COCO. Likewise, we'll look at the inner one here, and it's comprised of 16, 0 through 3, 30 through 3F is 16, so 16 times 8K, 130,1072, or 20,000 hex, divided by 1K is 128K machine. Now we're only going to be interested in this small inner block in here, because a COCO 128 and a 512 machine, they're exactly the same in this area. The only difference in the 512K is it has extra memory, and we're not going to deal with that for quite a while. All we're going to do is deal with this intersection here. Okay, again, 128 and 512 are exactly the same. You fire them up and they all look the same, and these 16 blocks comprises that 128K. Okay, just to review, this is what we did in our very first slide. This is where everything is located at. I know we're still not getting unconfused, but we're going to try it. So when we look at that basic low level, here's what we've got. And these are our MMU registers, okay? And they start at FA00, and we'll put block 38, block 39, 3A, except up through 3F. Right? Remember, these are blocks where that column was the physical memories. Was it 3F? Is a little. We're going to get there. Now, what we had told you early on in that one slide, we select whatever we want and put into these registers, and that's what we'll be actually pointing to. Now here I've used disk basic, which is at physical 3E. Also put it down here, which means we have disk basic in both of these address ranges, C0 to DFF and 40 to 5FFS. Now, it's easy to say, oh, I have a copy of disk basic down here. And I in a lot of my comments in my program, I say, get a copy. It's not a copy. It's the exact same physical address. Okay, physical address means that what memory you can put in your hand, this is pointing to that. Okay, but when you address it, it's here and here. Maybe the next slide it cleared up. Anyway, well, what this is, slow down on this slide here. If I was to poke something at this address C00, I would see it also down here at 4000 because it's changing the same physical address. If I looked at here, they would be the same no matter what I changed. If I changed something in the middle here, let's say at address 5000, it would also be changing up here at D000. Okay. We don't want to do that. You wouldn't want to change something down here and change the middle of just basic because it disaster results. Okay, this is just an example showing you what you could do and how these two addresses are the same physical address. Okay, hopefully this will clear some of it up. Here's our high memory. This is the highest memory we've got on either machine, 128 or 512. They both have this high memory of 7E up to 7E which is the highest memory. Okay, and it come across, we'd have that's at block 3F. But when you look at it in your program, it's E00 to FFF. Likewise, disk basic, it's block 3E, which its real address, physical address is 7 Charlie 000, and you address it at C00 to DFFF. Well, remember we poked or stored 3E down here in this MMMU register number 2, so it also is physical address is the same as one up here. So whatever we see at 4,000, we see at C00. Again, we wouldn't want to do that. Okay, but this is just an example to show what we're talking about. The physical memory over here, when you do something here, the MMU is actually putting out here in this physical, but you also see it down in this particular address range. Now, quick basic program. Again, this isn't quick basic. I should say a basic program you can write quickly. All right, we're going to print, we're going to peek at address 4,000. Before we back up one, before we change anything down here, we're just here still says 3A in here. We're going to peek what's at 4,000 and print that out. Then we're going to poke in that MMU register. We're going to poke that 3 easy, and now we'll be actually pointing to disk basic. We will print, we'll peek again 4,000, print that out, and we'll put the 3A back in there to restore it back to normal. We'll peek again and look it out. I said run. First thing that turned up was 205. Just some garbage that was out at address 4,000. And by the way, that was, I think it was CD, a hex CD. Just some garbage. We poked our 3E in there, and we printed out again. It's got a 68. Well, if you look in your ASCII table, ASCII 68 is capital letter D. Okay, well, if you're familiar with disk basic and you look at the very first 2 bytes of disk basic, which is normally at C00, you'll see a CK, stands for disk basic, DK. Okay, so when we did that, we got the D at that very first position. We restored it back to our 3 able, which it should be, did a peek and print it out again, and it's back to normal. Just showing you when you switch them registers around, you'll get the results. That's the results we was expected to get. You wouldn't want to do this with disk basic or extended basic, but it's an example. Another example, go to a 32 character screen and type this one in. All right, we want to poke at that same FFA2 in that register, a hex 38. Then we want to do a little loop for I equals 0 to 20 and poke at ampersand 4,564 plus I, comma 65. Well, 65 is in capital A. Then we do a next I. We want to do that 20 times and then poke to take it back to normal. And what you'll get is right below when you run it, you'll get all these A's across the bottom of your screen. Well, if you know your regular basic 32 character screen mode, the actual screen address is at hex 400 to 5 FFF. So if you wanted to do this without doing all these pokes and that, you'd want to print on a screen, you would do it at hex 564. But what we've done, we've also duplicated that in the MMU register up at address 4,000, so that's why we've added 4,000 to it. And that looks something like this here. Our physical memory is down here. For our system memory, where our screen is located inside here, 400. We duplicated up here at 4,000, and now our screen is in the middle here. And what that means is all it does is tell the MMU, but when it's set up, it knows to print the screen from inside here. Okay, it's another long story that we're not going to get into today. It just knows that that inside here is where that low-res screen is. And all we're doing is changing it up here, but also you can see it here. Confused? Good. You'll go back and look at this video again. Now let's see what the blocks look like. This is our HAM 128K when you start the machine up. All right, for the top, our same stuff, extended basic, disk basic, etc., down to our system work area, okay, which is our normal 64K, the same blocks we was using, 3.8 through 3F. Now, in the other 64K, we have this other stuff down here. Well, let's see what's in it, some of that stuff is. Okay, in hex 30 through 33 is the high-res graphics screen. If you're in basic and you say H screen 2, H screen 2, the extended, super extended basic will set it up for you. It will tell the MMU that starting at this physical address where this block is located, and for the next, these 4 blocks together, is what you want to display on the screen. This is the graphics screen, and these screens here, these 4 blocks need to stay contiguous, okay? You can't split this up and put one of them up here and one down. They have to stay together because your display screen is within these 4 blocks. You can move them someplace else, but tell the gimme chip that, hey, I've moved these blocks and it's now here, but they have to stay together for the graphics screen to display on the screen. We will do that much later, not the near future. Okay, the next part is if you're doing basic programs, you do an HGet or an HPut, that's this in this physical memory or block 34. Okay, when you're in high-res graphics mode, the system stack, which normally, remember, I showed you on the earlier slides, was down around 7F20. Well, whenever you in graphics mode, it's going to use this block here for the stack because it's going to overlay the stack with our graphics screen. Again, and that's futures. Next one is the high-res text screen. All right, that's what we're going to be working with here in the very, very near future. Okay, we've been doing it with our locate and our print line. Okay, well, that's what we was doing. We was telling BASIC to change this physical stuff in here because the gimme chip knows to display the screen coming in this physical memory at block 36. So we're going to move this, not copy, we're going to address this block up in our normal 64K, and then we're going to do our own locate and print directly to that address, that high memory address, via the gimme chip. Okay, so we're going to do something like this. We're going to store or poke, which are when you would call it yet, as you're learning, our 36 up in our MMU register. Okay, so that we're going to have a copier like we were looking at in the other slides. All right, last slide. I know it's been confusing and you probably need to go back through it, and maybe you'll get that light bulb will come on after piddling with it and looking at it and say, oh, I understand what that guy was talking about. The subject is key to what you're going to do in the near future, and you really need to understand if you're going to do assembly language programming on a Color Computer 3. If you're going to move them blocks around and you get into full graphics, you're going to move a lot. You're going to have to move a lot of stuff around and work a lot with the gimme chip. So there's a lot more subjects on this here. How to set the graphics up for the gimme, for the text screen, and there's more than 8 registers. Okay, there's really 16 registers, and they're addressed by task 0 and task 1. We're not going to get into that now. We'll get in at some other point. Hopefully this wasn't too confusing. I know it's a very confusing subject, and I will gladly take questions and try to answer best I can, because I learned the hard way, by looking at the actual code experimenting. I don't know how many times I rebooted my machine because I was testing out, trying to figure it out, and I just screwed something up and it didn't work. This was a long time ago, back in the 80s, but I learned the hard way. And you look at the unraveled code, and you can follow through there once you learn a little bit, and you'll see exactly what they're doing, and you get that aha moment. Well, go back through this lesson here, and I know we didn't do any code, so next time we're going to do some code based on the high-res text screen. So I'm done. Hope this has been informative, and we'll see you soon.